Account types can do a lot of work for you, but they're not dynamic enough to handle all of the security checks a secure program requires. This is where constraints come in handy. Constraints are another tool you may use to add security checks on the accounts being passed in to your program. Let's take a look at the anchor docs from the URL listed below. You can add constraints to an account with the following format. But let's look at constraints in action. Looking at the same code snippet that we used in previous videos, you can see the user account is utilizing the mute constraint to indicate that user should be a mutable account. My account is making use of 3 different constraints: init, payer, and space. The init constraint tells Anchor to create an account at this address. The way you would send a valid transaction to this program is you would have to pass in a public key to the My Account field that does not have a system account already initialized into it. If it does, Anchor will throw an error because it is trying to initialize a system account at this public key. If one already exists, it can't do that. The payer constraint indicates who is paying for the transaction fees and rent required to create an account. Here, payer equals user. So you are able to reference other accounts within an account struct in the constraint, which is pretty convenient. That is why this account is mutable, because the user account is paying for the transaction fees associated with this transaction, including the transaction fees and rent to create the account. The space constraint tells Anchor how much space to allocate on the account's data field. The required space is dependent on what is being stored. And here it is 8 plus 8. The first 8 is an Anchor-specific feature called the discriminator. More on that later. And the second 8 is due to the My Account data struct, storing a single data field, a U64. And you need 8 bytes to represent a U64. Let's take a look at the constraint documentation for more info. Here's the link. Here's the init payer space constraint. And I want you to look specifically here. Note that when using the space constraint, one must remember to add 8 to just the size of the account discriminator. This only has to be done for accounts owned by Anchor programs. Now let's look at a few other interesting constraints. Account sign checks the given account sign the transaction. In the previous lesson, we just learned about signer account type that does the same thing. So why do you think there's also a constraint that verifies an account signed a transaction? Well, one feature of the signer type is that there are no additional checks on the underlying account, and it's recommended that you do not access the account's data. The account signer constraint allows you to verify the account signed a transaction while also getting the benefits of using the account type if you want access to its underlying data. Account mute. We've already covered this. It checks that the given account is mutable. If that account is going to be paying for any transaction and rent fees, then the amount of LAM ports stored by the account will change, but it has to be mutable as well. Account owner checks the account owner and matches the expression. For example, you could check that the account owner is equal to a public key of a program for another account public key. See, owner equals token program.key. Has one. Checks the target accounts field on the account, matches the key of the target account field in the account's struct. Here you can see 2 accounts, data and authority. Has one checks that there is a field named after the authority account on the data account, and the data stored on that account is equal to the authority account's public key. One final one to look at today. Constraint equals expression is a constraint that checks whether the given expression evaluates to true. Use this when no other constraints fit your use case. There are several more constraints defined in the docs. So follow the link and read on.